Welcome back. We're in section 312. We're going to be talking about the connections, multiple representations. It's really just emphasizing that connection between these exponential functions and the geometric equations we talked before. So we're talking about the bouncing ball. We've done that before. So they're showing part of the table. So they want us to find the rebound ratio. Now the rebound ratio is really just our multiplier. So to go from 84.5 to 67.6, we're multiplying. So 84.5 times B equals 67.6. Divide both sides by 84.5, and you'll get B equals 0.8. So our rebound ratio is 0.8. Now, we need to find the initial height as well. We need to go back. So each time we're going to be dividing by 0.8 to go backwards. So 84.5 divided by 0.8 is 105.625. We got to go back again. So it's 105.625 divided by 0.8 because we're going backwards. And that's going to be about 132. So there's our initial. And that's going to be 132. So these exponentials, y equals a times b to the x. A is our initial and b is our multiplier, in this case the rebound ratio. So y equals 132 times 0.8 to the x. The initial is 132, and our multiplier, our rebound ratio. So we've done this before. It's just re-emphasizing. It's another way to look at these. So for B, major technology company, Expo Grow, they're growing fast. Y equals 3 times 4 to the x, where y is the number of employees and x is the number of years since the company was founded. How many people founded the company? Well, we know for this exponential, 3 times 4 to the x. The initial is A. It's that first number. And our multiplier is 4. So what we have is the initial is 3. We have 3 founders. Now, the growth of this company, we're multiplying by 4. So the company quadruples. You multiply by 4 each year. So if you kind of look at it, year 0, we had 3. Year 1, we're multiplying by 4, we have 12. Year 2, all the way up to 48. You can see we're quadrupling each time. Problem C. A virus is infecting these computers. Now you can see we're not subtracting the same number. So it might be an exponential function. So when we look at it, we need to find our multiplier. 27 times b equals 18. Divide both sides by 27. B equals, and I'm just going to reduce this fraction to be 2/3. Let's keep and see if that still holds true. 18 times b equals 12. Divide both sides by 18. B equals, once again, 2/3. 12 times b equals 8. Divide both sides by 12. B equals 2/3. So this is exponential. So now we know our multiplier is 2/3. That's how many computers are not being infected, because we have the uninfected computers. So now if we look at the questions, how many computers are in the Technology Center? We have 27 computers total. You can see that the term 0. What portion of the computers is infected? Now, we have 2/3 are uninfected. So that means 1/3 is infected. What portion is infected, and how many computers will remain virus-free by the end of the 3rd day? So by the end of the 3rd day, we have 8 computers, 8 virus-free. Now, if you're looking at as being the beginning of the 4th day, what you would do is you do 8 times 2/3 to the 4th. And you would have about 1 that would be uninfected. You get a little bit over 1, but as soon as a partial is infected, the whole thing is infected. That's not what that is. It's 27 times 2/3. Excuse me. We'd have 5. So you'd have 5 at the beginning of the 4th day. Now, as part of a major scandal, it was discovered that several statements from that Expigo in the beginning, they had 5 founders and they doubled each year. So y equals a times b to the x. Now, if they had 5 founders, a, our initial, is 5. And if we're doubling, our multiplier is 2 to the x. That's what the equation would look like. So just a real quick recap. A is the initial, and b is the multiplier. Now, A is that y-intercept. It's always going to be at 0 and a number. You can also think about in context, it's our starting value. So if it says it begins there or whatever. And how can you determine B? B is the multiplier. B is that multiplier. It's what we're multiplying by to get to the next number. So we're going to graph a few of these. Y equals 20 times 3 to the x. So these are changing from the ones we talked about last time because now we have a multiplier, or we have that initial of 20, not 1. So for -2, -1, 0, 1, and 2. We'll put a 3 on there as well. Now you'll have 20 times 3 to the -2nd is 20 times 1 over 3 squared, which is 20 times 1/9, which is 20 over 9. 20 times 3 to the -1st is 20 times 1/3 to the 1st, which is 20 over 3. 20 times 3 to the 0 is 20 times 1, which is 20. 20 times 3 to the 1st is 60. 20 times 3 squared is 20 times 9, which is 180. And 20 times 3 to the 3rd, 3 to the 3rd is 27, times 20 is 540. So that's why I didn't include a graph here, because we'll have to draw our own. Now the numbers are pretty big. I'm going to go up by 100, 200, 300, 400, 500, and 600 all the way up here. So we're at 160 to 180 and 3 all the way up to 540. So you can see it still has that horizontal asymptote at y equals 0. And that's what the graph looks like. That horizontal asymptote, HA, is at y equals 0. The domain, all real numbers. The range, in this case, y is greater than 0. The x-intercept, still none for this. And the y-intercept is now at 0 and 20. We can see that from the table. When x is 0, y is 20. Let's do another one, a little bit smaller, 1/2 times 2 to the x. -2, -1, 0, 1, 2, 3, and 4. So it's 1/2 times 2 to the -2nd. It's 1/2 times 1/2 squared. So it's 1/2 times 1/4, which is 1/8. 1/2 times 2 to the -1st, it's 1/2 times 1/2, which is 1/4. 1/2 times 2 to the 0 is 1/2 times 1, which is 1/2. 1/2 times 2 to the 1st is 1/2 times 2, which is 1. 1/2 times 2 squared is 1/2 times 4, which is 2. 1/2 times 2 cubed is 1/2 times 8, which is 4. 1/2 times 2 to the 4th is 1/2 times 16, which is 8. Now there's still that horizontal asymptote at y equals 0. And the graph will look like this. So the horizontal asymptote, HA for short, y equals 0. Domain, all real numbers. Range, y is greater than 0. X-intercept, there's still none for this one. And the y-intercept is now at 0 and 1/2. That is it for section 312. I will see you in the next video.